Okay, so we wrote a simple script in MATLAB in order to determine the root of a function. Now the point is, we are talking about the bracketing methods in general. So what are the bracketing methods? Basically, we are looking for a root within an interval. And of course, these algorithms may fail in some cases. So what are those cases? For example, there may not be any root within the interval that we are looking for. So this is one thing that we can check by using a graphical method. And the other thing, yes, we may have one root within an interval. And the other thing is, maybe there may be more than one root within the lower bound and upper bound that we are looking for. For example, we may have two roots within the interval, and we may have three distinct roots. In fact, all of the techniques that we are going to talk about is suitable for the functions which are continuous in general. Okay, so let's look at the bisection method first. So what's the bisection method? Now here we have the Poseidon algorithm. So first thing that we do is we determine the lower and upper bound for the function, for the x-axis, and then we evaluate the function at these points. Of course, if this is negative, this means that one of the bound is on the either side of the root and the other one is on the other side of the root. Okay, so this is one thing. So what we do next, then we take the mean of these values. We calculate a new position and we take the average. So basically we draw a line between these two, and then we evaluate the function at this new point, and we check if our new point xr is different side of the axis compared to the fxl, let's say. So their multiplication will be negative. Okay, so you can think like this. For example, here xl is here, xu is here, so as a result f of xl is negative and f of xu is positive, so it's negative. The multiplication of these two values will give us a negative value. As a result, this means that function crosses the axis, okay, x-axis, and possibly we have a root if the function is continuous. Of course, it is the same here, and it is the, well, this is a little bit a pitfall. In fact, you will find a different value here, but anyway, so this is the algorithm, and then we say that okay, then the root lies in the lower subinterval. So what it means, now xr divides the region xl and xu into two separate parts. So if this multiplication is smaller than 0, this means that f of xr and f of xl is on either side of the axis, and certainly the root is between xl and xr. Then we set the upper point xu as xr, and then we do the step 2 again. Okay, If XL and XR is positive, this means that f of XL and f of XR is on the same side. Basically, this means that the root is on the upper subinterval. So we set XL, so the lower bound, as XR and go to the step 2. So if f of XL and f of XR is equal to 0, so this means that XR is the 0 because it is near point, and as a result XR is the root. So you find the root. This is the termination criteria. Okay, so you can check it like this here. For example, a function crosses the axis, x-axis, and here is the root. So in the first iteration it is in the upper subinterval, then it is in the lower subinterval, or it may be in the lower subinterval, and then you may find the root. So this is the graphical representation of the bisection method. So each time you update, so in the first case, so we look at this interval, right, and we take the mean, so the mean is here, and we check it, and certainly XU is, f of XU is negative, f of XR is positive, so you change the subinterval XL as XR, or if this is your interval, basically the mean is somewhere here, right, and you check the mean value. Again, f of XR is negative, f of XL is positive, and then it's negative, and you check, you get the lower subinterval, you just change XR as f of XU, and then you reach to the root as a result. Here we see the Poseidon code, okay, for the bisection method. Let's check it step by step. So first we have the function. Our inputs are XL, XU, error, bound, IMAX, XR, iteration. These are our variables. Then we set iteration is equal to 0, and then we do the loop. First we create a dummy variable XROld, which is equal to XR. XR is equal to, our new point is equal to the average of XL and XU. Then we increase the iteration with 1. If XR is not equal to 0, then we calculate the relative absolute error. That's okay. Then we create a dummy variable test. This test variable is nothing more than multiplication of fxl and f of xr. F is our function. If test is negative, so upper bound is equal to xr. If test is positive, lower bound is xr, and then otherwise the error is 0, and then we check the error. If the error, approximation error, is smaller than bound for the error, or the number of iterations that we reach is bigger than our limit, maximum iteration, the limit for the maximum iteration, then we stop the evaluation of the function and then we exit. We will do this. We will write a code in order to find the root of a function by using bisection method.